Hello everyone, this lecture is about the two-port network. We will introduce some important concepts. The first is a port. As we know, in circuits, elements or networks are connected to the external circuits through terminals, but not any two terminals can form a port. The condition that two terminals can form a port is that the current flowing into one terminal must be equal to the current flowing out of another terminal. It's called the port condition. You should pay attention to this. With the concept of the port, it's easy to explain the two-port network. As its name implies, if a network connecting to the external circuit is with two ports, it's called the two-port network, or two-port for short. This is a two-port network diagram. In our course, we only discuss a linear two-port, which means that there are only linear resistors and linear dependent sources instead of independent sources in the network. Now we suppose that this is a two-port network N, which is connected to the external circuit through port 1 and port 2. If a new branch of a resistor R is connected between port 1 and port 2, do you think N is still a two-port network? To analyze whether it's a two-port network or not, we only need to check whether the current flowing into this terminal I1' is still equal to I1, and whether the current flowing into this terminal I2' is still equal to I2. If yes, it's a two-port network. If not, it's not a two-port network any longer. According to the generalized KCL, terminal 1,1' and the terminals 2,2' still satisfy the port condition, which means that the current flowing into terminal 1 is still equal to the current flowing out of terminal 1'. Applying KCL to this node, I1' should be I1 minus I. In most cases, it isn't equal to I1. Similarly, apply KCL to this node, I2' should be equal to I2 plus I, not be equal to I2. For terminals 3 and 3', the current flowing in isn't equal to the current flowing out any longer. Terminal 4 and 4' are the same case. The current flowing in isn't equal to the current flowing out any longer. So N is not a two-port network any longer. And the theorem and the analysis of the two-port network is not applicable for N any longer. You should remember this. Here is a general conclusion. New branch should not be connected between the two ports, otherwise it may destroy the port conditions, and the original network will not be the two-port any longer. The word may means it may not destroy the conditions sometimes. The following example shows the port condition hasn't been destroyed when a new branch is connected between the two ports. Let's see a special two-port network, the three-terminal network. It's connected to the external circuit through three terminals. The current flowing into terminals 1 and 2 are I1 and I2 respectively. Then the terminal flowing out of terminal 3 is I1 plus I2. Change terminal 3 into a common terminal. Terminals 1 and 3' form a port condition connecting to the subcircuit N1. And terminals 2 and 3" form another port connecting to the subcircuit N2. Based on the generalized KCL, the current flowing out of terminal 3' is I1 and the current flowing out of terminal 3" is I2. Redraw the network like this. It's a common two-port. If there's no other branches connected between N1 and N2, it's no doubt that the three-terminal network can be considered as a two-port network. But if N1 and N2 are connected by many other branches besides 1 3' and 2 3", that is, another branch of resistor R is connected between N1 and N2, will this three-terminal network still constitute a two-port network?